All right, and welcome back. We're going to continue plowing through Unit 5. Like I said last time, there's a bunch of problems I'm going to dismiss because it's a lot of 098 content, but actually we're getting pretty close to the 104 content. So I think we'll probably only spend like 10 more minutes max on the, recap of what we did last semester. So let's pick up where we left off. That is on page 5. I want to do one more substitution problem with you before I move into elimination, before I move into 3x3s. So let's check it out. Cool. So we looked at, no worries, Oliver. Thank you so much. We looked at example A, where we noticed it was already set up where y is 2x plus 4. Well, if you were told that a variable had a specific value, wouldn't you just plug in that value into the other equation because it's a system? Yes, you would. So we essentially would be replacing this y with our 2x plus 4. We're making that substitution, and I have it written here. So we have 2x plus 4x equals 2, and then we combine like terms and solve. Once we found our x coordinate, which by the way could have been our y, but once we found our x coordinate or one of our unknowns, we always want to plug back into one of the original equations to find the other unknown. My advice to you is always plug into the ones that are easiest. For us, I would say the y equals 2x plus 4 is the easier of the two because y is already by itself. So all you have to do is sub in for x and solve, and bam, you have your y. Take a look at part B. We have a minus 3 is equal to 3b, and then you have 4a equals 9b plus 12. Does anyone see the easiest path, like the path of least resistance? What may be a helpful strategy to use here?
Add the 3 on the first side.
Yes. Awesome. That's exactly correct. So in your mind, you're saying, well, I can easily get a by itself. If I add the 3 to both sides, I now have that a is equal to 3b plus 3. I totally agree. In one step, you've isolated a. So what we're going to do is take our second equation, which is 4 is equal to 9b plus 12, and all of our contents for a will go into a in our second equation. We're going to make a substitution. This is going to give us 4 parentheses, 3b plus 3. Always use parentheses when you're making substitutions. And then, of course, we bring down the rest of the equation. At this point, we just distribute and solve. We have 12b plus 12 equals 9b plus 12. Always move the variable terms first. This is something I stressed time and time again last semester. So we're going to subtract 9b first. That gives us 3b plus 12 is equal to 12. Naturally, if we move a term from the right to the left, chances are we have to move a term from the left to the right. It's that algebra dance. We're going to subtract 12 here. We have 3b is equal to 0. That is not a big deal. And then we divide by 3. 0 divided by 3 is valid. That's just simply 0. So I would take one of my original equations. Let's use a minus 3 is equal to 3b. And I'm going to replace b with my value. I know that b is 0. So a minus 3 is equal to 3 times 0. A minus 3 is equal to 0. And then, of course, add 3. And voila, we found both a and b. Recall that your solution must be written as an ordered pair. In this case, a comes before b, so we're going to write 3 comma 0. And that's your solution. Done. That's substitution in a nutshell. Let's turn the page so we can remind ourselves what it looks like to do elimination. So I've provided to you steps on how to use elimination or addition method. It means the same thing. You can view these at any point. But again, this is a recap or a reminder, a refresher of what we did last semester. So I'm actually going to skip part A because A is already set up for elimination. I actually want to look at part B. When we look at part B, we have 5x plus 4y is equal to 6. And then we have 2x plus 5y is equal to -1. The idea behind elimination is that you have the authority to choose a variable you would like to eliminate. So let's say that we're all on the same page and we would like to eliminate x. Notice in my first equation, I have a positive 5x, and in my second equation, I have a positive 2x. Recall that in order to get these to eliminate each other, they must be opposites. Think of the fact that 2 plus a -2 equals 0. Negative 3x plus 3x equals 0. 10x minus 10x equals 0. Are you getting the picture here? You have to create opposites. So immediately what I'm going to do is I'm going to say to myself, well, if I find a common multiple and ensure that one of these is positive and the other is a negative, then they'll definitely eliminate each other. So the number I want these to both become are 10x and -10x. That's my goal. So I'm going to write the goal here. So it's 10x and -10x. That's what I'm looking for. Having said that, that means I can multiply the entire first equation by 2 and the entire second equation by -5. Keep in mind that I did not have to multiply by a +2. I could have multiplied by a -2. And if I multiplied by a -2, this one must be a +5. They have to be opposites. As always, we distribute throughout. So I like to draw the lines of distribution because I don't want you to forget that you're multiplying every term in the entire equation. I always like shifting my work to the right. So I'm moving to the right along my page. So that gives me 10x plus 8y is equal to 12. Distribute the -5, we get -10x minus 25y is equal to +5. Double check your math. When we hit the 3x3s, it becomes like 10 times more crucial to pay attention to the tiniest details. When you are dealing with 3x3 systems, which we will do in like 5 minutes, the tiniest mistake can change literally everything. And then the idea of, oh, let me go and hunt and see where I went wrong is a bad idea, because that's going to take so long. For 3x3s, chances are you're going to want to scrap it and start again.
Can I see your math again?
Yeah.
Oh, there's a negative there.
Yes.
Okay.
I know, it's a tiny little guy.
No, I mean on the 5.
Oh, yes, yes. So
I
I had to include that negative just so that they can be opposites.
No, I didn't see things. So I'm sitting here, I'm like, where the hell did she pull -10 from?
Awesome. Yeah, I know, it's kind of squeezed in there. But perfect. Okay, so we've distributed, and now we can combine our equations in column form. Notice 10x minus 10x, they eliminate each other, which is your goal. So you can say, yes, okay, that was a success. Then we have 8 minus 25, or in essence, 8y minus 25y, which is -17y. And then we have a +12 and a +5. So when we combine those, we get a +17. Believe what the signs are. Sometimes I have students that are like, is that 12 minus 5? And then I have to say, well, what are the signs? And you would respond with, oh, they're both positive. Believe what the signs are and do that math, okay? Let's finish this off by dividing by -17, and we see that y is equal to -1. Perfect. So now that we have found one of our values, we do the same process we did with substitution. So we take one of our original equations, let's go with 2x plus 5y is equal to -1. And where we see a y, we're going to replace it with -1 because we solved for it. So we have 2x plus 5 times -1. And let's go through the motions. We're going to simplify. We add 5 to both sides. We get that 2x is equal to 4. We divide by 2, and we find x is equal to a +2. So always write down your solution as an ordered pair. So in this case, my solution is 2 comma -1, and you're done. There's elimination. This is a 2 by 2. Okay, so here's elimination. Okay. Technically it's a 2 by 3, but whatever. All right, let's turn the page. Here's more practice with the same exact stuff. For your reference, I would always multiply by the LCD to cancel fractions first. So for instance, just to clear out fractions, I'd multiply every term by a 10. So if I multiplied every term by a 10 to clear fractions, remember, we're just clearing fractions, that's all we're doing. This would give us 5x plus 2y is equal to 40. And then my LCD for this second equation is a 3, right? That's the only denominator that's the same. So 3 is obviously going to be my LCD. And that gives me -3x plus 4y is equal to 28. Once I have my setup in this form, I would then use elimination from here. Okay, I just wanted to show you the very first step, which was you should clear fractions. And then, of course, go through the motions. So let's move on because this is all 098 content. So is part D, that's 098 content. As a reminder, if you arrive at a false statement, the system is inconsistent, which means there are no solutions. If the statement is always true, the system is dependent. And in which case there's an infinite number of solutions. Okay, keep that in mind. A false statement would be something like, I don't know, 3 is equal to 5. And you'd be like, no, that's absurd. When will 3 ever be 5? And then a statement that's always true is something like 4 is equal to 4. Okay, that's a true statement. It could even be an equation that that sometimes, like, I guess, bypasses our minds. So for instance, if I was looking at, a system and I noticed that we ended up with, I don't know, like 2x plus 5 is equal to 2x plus 5, something like this, that's also a true statement. You don't need to go further from there. It's exactly identical. It'll always be true. Okay. We are now ready to solve systems of equations in 3 variables. I'm very excited about this. Take a look at your first system. This is a nice, gentle way of diving into systems with 3 variables. What's jumping out at you?
The x equals 4.
Yeah, so Jimmy, you're like, I am already given a solution. Jimmy, out of curiosity, what would you do with that x is equal to 4?
I mean, because you have the question that's right above. It says which method would be best to solve it, and what pops up in me was the x equals 4, and since that variable is already equal to something, I'm going to try to use substitution to do that.
Yes, I love it. Great idea. So out of curiosity, where would you substitute that x equals 4?
I guess in the equation, you can do both of them, right?
You can.
I would have anything with x in it, basically.
True. I love it. I love it. So Jimmy's saying you can replace x in either equation with a 4. So why don't we do that and see what happens? So we have 2x plus y equals 3, but instead of that x, we're going to replace it with 4. So I have two. Go for it.
Wouldn't you just do it in the first equation because you only have one variable to solve for, and in the second one you have 2?
Okay, so some are saying, let's be a little strategic about this. If we focus on just plugging in the 4 here, we can plug it in here too, but she says if we focus our efforts just plugging it into the first one, that'll allow us to also find y. And then once we have 2 of the unknowns, 2 out of the 3, that's when we can plug into the third equation to find the third one. Yes, I think that's a great strategy. Either way is going to work because it reveals itself to us the path that we have to take. So notice that now I know that x is 4 and y is -5. So because I have these two, x equals 4, y is -5, I'm then going to plug into my third equation so that I can find z. So we have 3 times x, and x is 4, plus 5 times y, and y is -5, plus 6 times z is equal to -1. Perfect. I like this flow because you're building on your solutions. So we have 12 minus 25 plus 6z is equal to -1. My advice all the time is to combine like terms that are on the same side. So cleaning these up, that gives us -13 plus 6z is equal to -1. Go ahead and add 13 to both sides. 6z is equal to 12, and then divide by 6. So we find that z is equal to 2. We must write our solution this time as an ordered triple. Okay, so we have 3 solutions, x, then y, then z. X comes first, then -5 for y, and 2 for z. And there is your solution. This one was really, really nice because we were given one of our answers already. So we said, yeah, substitution would make the most sense. Excellent. Thank you, Jimmy and Summer. That was awesome. Let's turn the page and look at something a little more complicated. Okay. Let me describe to you the best way to think about these equations. Okay. Because we are starting with a system that has 3 equations and 3 unknowns, you're going to want to follow this flow. Take 2 of the original equations and eliminate a variable. Take another 2 of the original equations and eliminate the same variable. What ends up happening is that you have 2 new equations that both have the same set of variables left over. So like for instance, if you eliminated z from each of your original pairs, you'll have 2 equations that both only have x and y, x and y. Once you can break down that 3 by 3, that 3 equations and 3 variables to 2 equations and 2 variables, then you're right back to where we were in 098. We just have to focus on that first step. Once you have your 2 equations with 2 variables, you eliminate or substitute. You're probably going to want to eliminate and solve for one of your unknowns and then work backwards. If you have 2 equations that both have x and y, and let's say you solve for y, plug that back into the equation that has only x and y, kind of pointing at to what Summer said. You want to plug it into the equation that's going to give you another answer. So if we take that x or that y, whatever we find our value of, and we plug that into the equation that only had x and y, then we find x. And once we have x and y, we plug it into one of the original equations that has x, y, and z, because that's going to help us to find z. So we go from 3 equations to 2 equations to 1 solution, plug that back into a 2, plug that back into a 3, and you've solved your system. The reason I feel like if you look at your page, you'll notice you have a ton of space. You'll need all of this space to do this work in solving the system, okay? But keep that in mind. Manipulate from 3 equations, you want 2 equations with 2 variables to solve for 1, right? Solve for one of the unknowns, plug that back into a 2, take those 2 solutions, plug it back into a 3, and then you'll solve. Let's check it out. So I have x minus y plus 2z is equal to 6, 2x plus y plus 2z is equal to 5, and then x plus 3y minus z is equal to -4. May I please have a volunteer offer up a variable they would like to eliminate?
Start with X.
Okay, so Shane says, let's eliminate X. I'm going to start with my first equation, X minus Y plus 2Z is equal to 6. I urge you to write small. And I'm going to take this second equation and I'm going to write it directly underneath it. So we want to eliminate X. Notice I have a positive 1x and a positive 2x. Well, a common multiple of 1 and 2 is 2. So our goal is to have a positive 2x and a negative 2x. We can do that by simply taking the first equation and multiplying by a negative 2. So let me go ahead and distribute and see what we get. We have negative 2x, positive 2y, negative 4z is equal to negative 12. The second equation can stay exactly as is because they are opposites already. So I don't have to worry about multiplying by any kind of coefficient. Notice our x's here are eliminated. And I'm left with 3y minus 2z is equal to negative 7. What I may do is highlight the equation that has just 2 variables in it. So I'm going to go ahead and highlight this equation. Oh, I knew it was going to smear. I was like, is it dry yet? Is it dry? No, of course not. Okay. So there's my first equation that has just y and just z. All right, let's go back to the drawing board. In order to derive this equation, I manipulated the first 2. I'm going to use a different pair this time, and I'm going to eliminate x again. This time, I'm going to use the first equation and the third one. So I'm going to go ahead and write x minus y plus 2z is equal to 6. And underneath that, I've got x plus 3y minus z is equal to negative 4. I want to eliminate x again. So I'm going to multiply this second equation. And again, only because I feel like it, I'm going to multiply the second equation simply by a negative 1. If we make one of them negative, then that means they're opposites. So we're golden. I'm going to rewrite the first equation, x minus y plus 2z is equal to 6. And then I'm going to distribute the negative 1 throughout the second equation. Negative x minus 3y plus z is equal to positive 4. I can now combine both of these equations and notice that x is eliminated again. That's exactly what we were looking for. This leaves me with negative 4y plus 3z is equal to 10. Perfect. So I have my second equation that has the same exact 2 variables. See, guys, I'm learning. I'm using a box instead. Take these 2 equations and stack them because this is our new system. So we went from 3 equations, 1, 2, 3, to 2 equations. So let's write those together. 3y minus 2z is equal to negative 7. Negative 4y plus 3z is equal to 10. Beautiful. This time, someone else, which variable would you like to eliminate, y or z? Shout it out. Z, okay, we'll go with z. So one's already a negative, the other's already positive. Our first one's a 2, right? Our second one is a 3. So we want them to become a common multiple, which is 6. So I'm actually going to multiply the first equation only by a 3 and the second equation only by a 2. I don't need to worry about multiplying by a negative number because the signs are already opposites. Let's go ahead and distribute. We get 9y minus 6z is equal to negative 21. Then we have negative 8y plus 6z is equal to 20. Keep in mind, you're distributing throughout the entire equation. Don't forget that, okay? We wanted to eliminate z, and we were successful. They cancel each other out. 9y take away 8y is 1y. Negative 21 plus 20 is negative 1. So I have just found one of my solutions. So I went from 3 equations to 2 equations to 1. Now I'm going to take my 1 and plug it back into one of the 2's. It doesn't matter which one we plug back into. So I'm going to go ahead and plug it into 3y minus 2z equals 7. So 3y minus 2z equals negative 7. We're going to plug that in for y. So we have 3 times negative 1 minus 2z is equal to negative 7. Let's go ahead and solve this. It's a negative 3. I'm going to add 3 to both sides. That gives me negative 2z is equal to negative 4. And then if I divide both sides by negative 2, I get z is equal to a positive 2. And here's my second answer. So now I have 2 solutions. I know y and I know z, which means at this point, I'm going to want to plug back into one of our original equations that has 3 unknowns so that I can find the missing variable. So I'm going to pick my first equation, which is x minus y plus 2z is equal to 6. And I'm going to go ahead and make my substitution. So this one goes in here. And then, of course, let's draw a dotted line so that we can follow the flow. And that one goes here into z. So we have x minus, careful, we have to sub in a negative 1, so we need parentheses. Negative 1 plus 2 times z, which is 2, and that's equal to 6. And then we solve. X plus 1 plus 4 is equal to 6. X plus 5 is equal to 6. Subtract 5, and we get that x is equal to 1. And there's your third solution. Make sure you write your answer as an ordered triple. So I'm going to say that my solution is 1, negative 1, 2. And now we're done. What are your questions? What do you think? If
This
you're
is
saying,
a lot of work.
you know, you all say that every time. Yes, it definitely is. But that's the content that we're in. That's the level of math skill that you are now in. That you can have a problem like this, which is a lot of work, and still be very successful at it. You should be proud. You should be proud of yourselves to be at this point where you could see something so complex and say, I can flow through this. Okay. So as a reminder, pick 2 equations, pick another 2, eliminate the same variable. Now you have 2 equations with the same 2 variables. Take these 2 and solve that system. Jimmy.
Yeah, the only thing I think that'll probably throw me off is when I'm doing the solutions. I might instead of one of the equations you made, I might take it from the original system. And I
Check
feel
this
like
out.
that's gonna throw me off.
No, Jimmy, if you take your answer here
Hmm.
and you plug it into one of these, you're going to be like, oh, shoot, I don't have enough information.
Okay. Oh yeah, because you still need 2 variables, right?
Yes. So
Okay.
you would say, okay, wait. Let me go back to the drawing board. You would say, if I know one of these and I have these 2 equations, which are highlighted, by the way, please highlight them, or, you know, do
Circle
something that
them,
draws
something,
attention.
yeah.
Yes. Do something that draws attention, and you could say, oh yeah, I got to plug that bad boy into one of these, because then it lets you solve for yet another one.
Okay, thank
All
you.
right. Yeah, you're welcome. It has a very logical flow. And I think Jimmy pointed out that, you know what, sometimes if you try something and you hit a wall, redirect, right? Say, oh, wait a second, hold on. There's a better strategy for this. Let me see what that strategy is. Okay. Very cool. Go ahead and turn the page. Take a look at our system here. And I would like you to try this one. I'm going to walk you through it a tiny bit just by giving you a little bit of advice. And actually, if you're all okay with it, I would like us to eliminate the same variables. What I'd like us to try to do is take two of the equations and then another two of the equations and eliminate y. Please start by eliminating y. So take two equations, then take another two and eliminate y first. All right, I'm going to pause the video and give you some time. When you find your solution, please type that into the chat. Send that to me privately. So I challenged you all to start by eliminating y so that we can all have the same result. Melina, excellent. And what I mean by that is so that when I show you the process, we'll probably have an identical setup here. So because I am charged with eliminating y first, I'm actually going to look at my second and my third equation. Do you see how these are automatically going to cancel each other out, which is really, really cool. I'm still going to rewrite this because I want to make sure that everything is nice and organized. So I'm going to write negative x plus 2y minus z is equal to 8. And then underneath it, 3x minus 2y plus 4z is equal to negative 6. So I took the second two, or the bottom two equations. Notice y's automatically canceled. I didn't even have to multiply by anything. So that leaves me with 2x plus 3z is equal to 2. So there's one of my equations that has two unknowns, x and z. I'm going to take another two equations. I'm going to use the first one and the third one. You didn't have to. You could have used the first and the second if you wanted, but I'm going to use the first and the third because they're opposite signs. So I've got x plus y minus z is equal to 0. And then I have, again, I'm going to take the first and the third one. So then I have 3x minus 2y plus 4z is equal to negative 6. I'm going to take the first equation and multiply it by a 2, so that way I can get these to cancel each other out. So this leaves me with 2x plus 2y minus 2z is equal to 0, right? 2 times 0, 0. I'm going to bring the second equation directly underneath it. I don't need to multiply by anything. And then notice that my y's cancel again, which is great. That leaves me with 5x plus 2z is equal to negative 6. I now have two equations that both have the same set of variables. Let's go ahead and use elimination on that system. So I'm going to rewrite my equations. We have 5x plus 2z is equal to negative 6. And I have 2x plus 3z is equal to 2. I'm going to choose to eliminate my z's. I have a 2 and a 3. I want them to both become 6 and a negative 6. So I'm going to multiply the top one by a, let's do negative 3, and the bottom one by a positive 2. Let's distribute and see what we get. So we have negative 15x minus 6z is equal to positive 18. Then I have 4x plus 6z is equal to 4. Notice my z's cancel each other out, which is exactly what I was hoping for. Negative 15x plus 4x is negative 11x. And 18 and 4 make 22. So when you divide by -11, we get that x is equal to -2. And there's one of my solutions. It only makes sense to take this answer and plug it into one of the equations that I have highlighted. Because if I know one of the variables, I can solve for the other one. So I'm going to plug it into this one. So we have 2x plus 3z is equal to 2. And I'm going to take this solution and I'm going to go ahead and plug it in for x right here. So we have 2 times -2 plus 3z is equal to 2, and let's solve. We have -4 plus 3z is equal to 2. Add 4. 3z is equal to 6. Divide by 3. And we get that z is equal to +2. So there's yet another solution. The last thing I have to do is take both of these answers and plug it into one of my originals. I'm just going to put in the top equation because that actually looks like the most basic out of the three. So I have x plus y minus z is equal to 0. Well, I know that x is -2. I don't know y, but I know z is 2. Combine like terms, y minus 4 is equal to 0. Add 4 to both sides, and we get that y is 4. So our solution as an ordered triple is going to be -2, 4, +2. Excellent work here. For those of you who shared your answers in the chat, excellent, excellent work. How did this go for everyone else? What were some of the issues that you had as you moved through? Would you kind of be willing to share that?
The first thing I noticed, like right off the bat, was that my addition was wrong, like getting the first set out of the first two equations.
Oh, shoot.
Where the 2x plus 3z equals 2, I did 2x plus 4z equals 2, and that messed everything up. Sorry.
Right there. Yeah, the tiniest thing.
Yeah.
Yeah, I would just take an extra second, especially if, if this happens, then just take an extra second and be like, wait a second, let me just verify -1, +4, +3. Okay, now I can move forward. Especially with these, because you're absolutely right. The second that one tiny thing goes wrong, it doesn't even matter about the rest. Everything else is wrong. It's pretty crazy. Thank you for sharing that. Any other places or potential areas that we should all listen to or focus on? Yes.
I mean, I feel like I messed up with this one. I mean, I feel like I maybe gotten the two solutions right.
Okay.
But the x was different when I got yours, or is that going to be?
What did you end up getting?
I got. Let me actually finish first. No, yeah, I found z first.
Oh, what did you get for z? Did you get 2?
No, sorry, not z.
Oh, you got x first.
Yeah.
Okay.
Yeah,
and if that x, if you didn't find that -2 initially, then that's it. It's a trickle effect after that, and it's like everything else is going to be slightly off.
I mean, I'll show you after, but because it's longer, I don't want to take time up. But
yeah, no, I understand.
Yeah.
And it really is just the smallest things, like especially in a case like this. So we just want to be really, really, really careful. Good. Let's take a look at example 9. I just want to hear your thoughts. Don't say anything yet. Just kind of look at this. Look at each equation. Think about it. What do you notice? Just kind of play around with this in your mind.
-z and +z. We can cancel that out.
Interesting. So Jose's eyes are drawn to this, which is actually really interesting. So let's kind of play around. So Jose says, let's take these two equations and let's combine them. So I have 3x plus z is equal to 7, and I have 3y minus z is equal to -1. You're right that the z's cancel. So what am I left with?
X and y.
3x plus 3y is equal to 6. Interesting. Okay, I like what I'm seeing. Any suggestion from here? What should I do?
You could take the first equation and then multiply that by like a -1.
True, except look what happens. If I take this first one and I multiply it by a -1, that is going to give me the opposite. But notice this one's x and z, but this one's x and y.
Oh, weird.
Right? No, that's okay. I like talking about this. We have to talk about this. What might be
How about x plus 5y equals 2? Can we take that one?
Let's look at that second equation. When I manipulated these two, right? I got 3x plus 3y equals 6, but I still haven't used this guy, the x plus 5y equals 2. So if I bring it directly underneath, I can see, oh, wait a second, they have the same variables. Now I can actually use elimination. Okay, what should I multiply by?
-3,
Yes, which one?
the second one.
Perfect. Let's multiply the second equation by -3 and let's see what happens. So we get 3x plus 3y is equal to 6. Distribute this 3 throughout, you get -3x, -15y is equal to -6. Perfect. Our x's are going to cancel. 3y minus 15y, that's going to be -12y. 6 minus 6 is 0. And then, of course, we divide by -12. And we get that y is 0. Okay, where would you like me to go from here? Let's go with Didia. Where should we put, and you get to choose. Where do you want me to put y equals 0?
Uh, 3y minus z.
Yeah.
-1. Yeah.
Nice. You actually read in my mind. I would have done that myself too, only because it seems like it would be the easiest out of the three, really, or maybe not. It doesn't matter. So I'm going to take the 3y minus z is equal to -1. And I'm going to go ahead and plug that in. So we have 3 times 0 minus z is equal to -1. That goes away. -z is equal to -1, which means if you divide both sides by -1, z is equal to +1. So now I have these two solutions, which means I just need to do what? What's the last thing? And this is for anyone. What's the last thing I should do?
Put those two terms into an equation and then equal.
You pick. Which equation should I manipulate?
First one, I guess.
Cool. So we have 3x.
Wait.
Why? No, trust yourself. You're right. We have 3x plus z is equal to 7. I know z. The only thing I'm missing is x. So if I do this, 3x plus 1 is equal to 7, I can solve for x. You were right. Trust yourself. 3x is equal to 6. Divide by 3, and bam, I've just solved for x. So my solution is going to be 2, 0, 1. And there you have it. I like that we explored our options and thought about, what things we can and can't do, or what things would be helpful or not helpful. This is the process you should go through as you work through these problems on your own. Be willing to kind of play around with ideas here. And don't feel like, if you hit a wall, that's it. That's it. You hit a wall, you can't go anywhere. Just go back to the drawing board. Have some faith in yourself. Good. I love it. Recognizing inconsistent dependent systems. Well, we've seen that with with systems that contain two unknowns and two equations. That can happen with a system that has three unknowns. So essentially, we're still watching for that same idea. What I'd like us to do this time is, why don't we start solving the system by eliminating Z? I would like us to do this one by eliminating Z. I'm going to pause the video so that you can have an opportunity to explore this one. Start by eliminating Z. So remember that we always want to start by taking two of the original equations and then another two original equations and eliminate the same variable. So because we want to eliminate Z, I recommend to take the first equation and the third equation. We could start there. Let's combine these and see what we get.
Because with my two new equations, they're the exact same thing, but one of them is opposite. One of the variables are just opposite of each other.
Yes, which is okay, which is totally okay. Let me show you. So I combined the first and the third equations, and I got 3x plus 4y equals -2. But we have to go back to the drawing board and pick another 2. I'm going to take the second and the third equation this time. So -x plus 3y minus z is equal to -3. -5x plus 5y plus z is equal to -1. We always have to take 2 and then another 2. Notice my z's naturally cancel out, which is really, really great. That leaves me with -6x plus 8y is equal to -4. So here's my second equation. I need 2 of them that have the same 2 variables. And we have that. So now I'm going to write them together. 3x plus 4y is equal to -2. And then -6x plus 8y is equal to -4. I want, yes, go for it. What's that?
Is it -3x plus 4y?
Ooh, thank you so much. This definitely should be a -3x plus 4y equals -2. Very, very nice. And then this one, -6x plus 8y. Yes, beautiful. Thank you for that correction. You're totally right. Which actually would have changed my answer. So I appreciate that. We are going to eliminate x's. So why don't we take the first equation and multiply it by a -2. If we multiply the first equation by a -2, this is going to be a positive 6x, which is exactly what we need. So let's see what happens. We get a positive 6x, a -8y, and then a positive 4. Now, if I write the second equation directly underneath it, what do you notice?
We can cancel x and y.
Yes, you can cancel both x and y. So that leaves us with 0. Notice 4 minus 4, that also leaves us with 0. What would your answer be in this case?
Would be inconsistent?
It wouldn't be
Or no,
Which one?
what was the other one?
We've got them right here, and we got.
Oh,
It's actually going to be dependent. So this particular system is dependent. As a reminder, we are left with a true statement. 0 equals 0. What this implies is that there is an infinite number of solutions, and that's what we would actually write for our answer. There's an infinite number of solutions.
hey, isn't inconsistent is no solutions, right?
Yes, and actually I'm
Yeah.
gonna write that directly here.
Oh, because I don't know why I thought 0 was not a solution, so that's why. Okay.
No, it can be. But let's say this was, I don't know, 0 is equal to 5. Then we'd be like, hell no.
Okay.
right? Because that doesn't make any sense. It'd be like somebody saying, hey, I know I owe you $5, but I'm just going to give you 0 because it's the same.
Okay.
I'm not going to
Alright.
pay you back
Yeah.
because I'm going to claim that they're the same value. With
Alright.
consistent, that means there is one answer. Like the systems that we just did on our previous pages, we found solutions. Like we found solutions to example 8 and example 9. Those are both consistent systems because they have a solution. With this guy, because we had a true statement at the very end, we knew this was a dependent system, so there's an infinite number of solutions. Very nice, very nice. Okay, well, that pretty much concludes the process for solving our system of 3 equations with 3 unknowns. When we come back from our 5-minute break, we're gonna look at what happens if we have a nonlinear system. Like, for instance, what happens if you have a term that's like x squared or y squared, or who knows? So we'll be back in 5 minutes. So I will see you at, let's round up, 10:17. See you back at 10:17. So we are now ready to look at what happens if we want to solve a nonlinear system graphically. So when I personally attack problems like this, I think about it in 2 ways. I want to figure out, you know, how to solve this algebraically, and then also how to solve it graphically, because sometimes it could be pretty tricky trying to graph these equations. So we're kind of better suited to use an algebraic perspective. But because we should know how to graph parabolas at this point, I feel very confident about looking at graphing these systems, okay, with you all. So take a look at our first one. We have y is equal to x squared minus 4, and then we have x plus y is equal to -2. Notice with our first equation, we have a parabola, right? We have a quadratic equation, which is a parabola. So we can take steps to actually graph this. So let's start off with what is the axis of symmetry. How do you find it? What's the formula? By the way, here, what's my A, my B, my C? Do you guys remember from yesterday? What's A, what's B, what's C?
A is 1,
A is 1.
B is also 1.
Does B?
Oh no, wait, this is why okay, I'm thinking quadratics. B is
Ah,
4
actually, you
or negative
so
4.
I like what you were saying about B and kind of trying to identify like what its value is. Believe it or not, because it is a quadratic equation, that B term is missing, which means B is 0.
Oh.
And that's okay.
Oh, it is a quadratic.
Yes, yes,
Okay.
absolutely. And then we have C is equal to -4. So if I wanted to start with the axis of, that's my dog, sorry. She just laid and rolled into my camera. So we have the axis of symmetry. We have x is equal to -b over 2a. But then we see that it's a -0 over 2 times 1. So x is equal to 0 is our axis of symmetry. So I'm going to say that x equals 0 is right here, right? Over the y-axis. Now I want to find my x-intercepts. So in order to find my x-intercepts, I have to make y equal to 0. And I'm probably going to have 2 of them. So if I make y equal to 0, how can I solve this? What strategy would help me to find my x-intercepts? What can I do here?
Complete the square.
Yes, we can complete the square. I love it. Give me another strategy. That will always work. Give me another strategy.
Add 4. Let's take the 4 over and do this. The
You're saying it.
slash into this line square root.
Yes, okay. Yes, that's another strategy. Bring the 4 over, do the square root property. I love it. Give me another strategy. That's 2 of them. Come on, what else are you seeing? Don't be shy. What else do you see?
Quadratic
Can you
equation.
use for quadratic formula?
Yes, the quadratic formula. I love it. There's actually one more technique that we can use. We can,
Factor?
yes, we can factor. What does this factor into?
X minus 2, x plus 2.
So Jose, what are my x-intercepts?
X 2
And
minus 2.
yeah, score. So I showed the factoring just so that we don't forget that that's an option. I didn't have to. I could have added the 4, taken the square root property. I would have found 2 and -2. I could have completed the square by bringing the 4 over and then taking half of b, which is 0, and then squaring it to both sides, which is 0, and then taking the square root property, which is positive and -2. Or I could use the quadratic formula. Any of those things would work. So I have my x-intercepts, which are 2, 0, and -2, 0. Perfect. And the last thing I need is a y-intercept. So for this equation, if I wanted the y-intercept, remember that we can only find that when x is 0. So if I make x 0, 0 squared minus 4 is -4. So my y-intercept is 0, -4. Let's go ahead and graph this as best we can. Here's that side. And here's that side. It's pretty good. Not too bad, not too bad. So all of that was for y is equal to x squared minus 4. We still want to graph x plus y is equal to -2. Give me a strategy for graphing this equation. What would you do first? This is a linear equation. How do you graph it? Twiggy, please stop, honey. Ooh, I feel like we are overwhelmed with the content that we just learned and we're forgetting the basic stuff. Let me show you. Start by subtracting x. If I subtract x, I have y is equal to -x minus 2. What form is this equation in? What's this called?
Y equals mx plus b.
Yeah, and what's the technical name for the y equals mx plus b equation?
Slope.
Slope.
Slope intercept.
Yes, slope intercept. Beautiful. Okay, what is my slope and what is my y-intercept?
Slope is -1.
Yes, score. I'm going to write that -1/1. That way it's a fraction. And what is your y-intercept?
0,
-2.
Yeah, 0. Wait, what was it? 0 what?
-2.
Yeah, score. 0, -2. So let's go ahead and plot the y-intercept, which is 0, -2. That's right here. And then we're going to apply the slope. The slope says fall 1, run 1. Fall 1, run 1. Let me go backwards. Aha. Okay, let's connect these with a straight edge and let's see what's happening. So graphically, it looks like I'm very confident about this one being a solution where both the line and the parabola seem to cross through the point -2, 0. So I'm going to say that that's one of my solutions, -2, 0. Now, when I look at this graph carefully, even though my u wasn't perfect, I feel like it's possible that 1, -3 is in fact another solution. We should always check because my graph is a little, off, and I want to verify that they're actually crossing here at 1, -3. So what I would do is I would test 1, -3 in my first equation. So if x is 1 1 squared is 1 minus 4. 1 minus 4 is -3. 1 -3 is in fact a solution. So we just want to make sure that what we see on the graph is actually what's happening. Okay, any questions on the way in which I graphed part A? Okay. All right, I don't hear any questions. So let's take a look at the second one. So this time I have two quadratic equations and I want to graph them both. For the first quadratic equation, this is actually in vertex form. This is in vertex form, which is super cool. So essentially, this form kind of looks something like y is equal to x minus h squared plus k, where k is your vertex. So something to think about. You don't have to like commit that idea to memory because you can essentially prove it, but I wanted you to know that that was essentially vertex form. Okay, so that that hk represents your vertex. So having said that, let me rewrite this equation. Y is equal to x minus 2 squared minus 1. What this tells us is that my vertex is +2, -1, because remember it's hk. So the equation is already x minus h. H in this case is 2. And k is whatever is after the squared term, so it's a -1. So I know the vertex here is 2, -1. So 2, -1. Out of curiosity, is this equation going to open upwards or downwards?
Up.
Yep, for sure. You know it's going to open upwards because your first term is positive. So when you open this up, x minus 2 times x minus 2, you'll get x squared. And x squared is positive, so it's definitely going to be open upwards. I still want to find my my intercepts. So remember, in order to find x-intercepts, we want y to be 0. So I'm hoping I have 2 x-intercepts. And where for each of these, y is 0. So let me go ahead and plug 0 here. Okay, perfect. Help me solve this. What might be the first thing we could do? What would you do? Phil, what would be the first step you would take? And remember, we're just playing around. So if you were like, maybe the first thing I can do is this, what would you choose?
Would you like write out x minus 2 twice and then like, could you distribute the -1 to it?
Well, I like what you said initially. You
Okay.
said, would you take the x minus 2 and square it out, like write it twice and then distribute? Yeah, you totally can do that. Yes. If you prefer that method, go for it because you'll open this up, but keep in mind what this says, blah, 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 -1, right? So if you do that math, just make sure to combine it with the -1 after you open all of this up. So that is an approach. You can do that. Give me another approach. What's another thing we can do mathematically? And this is for anyone. What's another thing we can do mathematically? Nung, what do you think?
Can you bring the 1 over and then like square root it?
Boom, very nice. Yes, that will work also. And it's going to take a little less time than opening this up. But as a reminder, you can. There's nothing wrong with opening this up, okay? So I'm going to bring the 1 over. So we have 1 is equal to x minus 2. This whole thing is being squared. And so what Nung is saying is let's use the square root property. If we use the square root, it'll cancel out the square. Remember though, when you use the square root, you have a positive and a negative solution. Don't forget that plus and minus right in front. So we have positive and negative, square root of 1 is 1. And then the square root and the square cancel each other out, leaving you with x minus 2. Let's go ahead and add 2 to both sides. So now let's do the math. We have 2 plus 1, which is 3. And then we have 2 minus 1, which is 1. So I've just found my 2 x-intercepts. 3, 0, 1, 0. I'm going to shift this over a tiny bit. 3, 0, 1, 0. The last thing I want to do in this case is I want to find my y-intercept. And recall that the y-intercept is found when you plug in a 0 for x. So for my y-intercept, if I plug in a 0 for x, then we've got 0 minus 2, and a negative 2 squared is a positive 4. 4 minus 1 is 3. I apologize, I didn't write it down. There's just so little bit of space here. Remember, just take that 0 for x, plug it in. 0 minus 2, that's a negative 2 squared is a positive 4. 4 minus 1 is 3. So 0, 3 is my y-intercept. Because we know the vertex is 2, negative 1, my parabola is symmetric about this line, right? The line always goes through the vertex. So if I'm 2 away from the vertex here at this point, then I'm 2 away from the, if I'm 2 away from the axis of symmetry here, I'm 2 away on the other side. And I like to draw the extra dot just so I can make the U pretty perfect as I can. So I'm going to go ahead and connect this. Here we go. And the other side. Okay, not bad. Not bad at all. We're going to do the same thing for our second equation. For my second equation, y is equal to negative x squared plus 6x minus 5. Is this going to be opening upwards or downwards?
Down.
Yes, absolutely. So we have a negative x squared, which means it's going to be opening downwards. So something to think about, we're going to have like 2 u's intersecting, one's concave up, one is concave down. Very nice. Let's start with the y-intercept. I think that's the easiest. So if we want the y-intercept, remember that x must be 0. If x is 0, this term goes away, this term goes away, and you're left with minus 5. So 0, negative 5 is my y-intercept. So I'm going to go ahead and plot that point right there. The next thing I need to do is find my x-intercepts. In order to find my x-intercepts, I have to make y 0. So I've got 0 is equal to negative x squared plus 6x minus 5. Shout out what technique you would like me to use.
Factoring.
Sure, I can try to factor. Let me see if it's possible. I'm gonna write in pencil just in case. The first thing we would do is we would actually divide out a leading negative 1. So I would divide every term by negative 1, and actually I can do that no matter what. So let's divide every term by negative 1. So that gives me 0 is equal to positive x squared, negative 6x, positive 5. So we want to find factors of a positive 5 that combine to give us negative 6. And actually, this is possible. So we know that 5 times 1 is 5, but negative 5 times negative 1 is also 5. And negative 5 and negative 1 give us negative 6. So it is factorable. So we have x minus 5, x minus 1, right? Because when you distribute, you get this polynomial, which means my x is equal to a positive 5 and a positive 1. So let's go ahead and put those in our x-intercepts here. 5, 0, 1, 0. So 1, 0, 5, 0. So far, so good. So these 2 points are on this parabola. The next thing we need is definitely a vertex. So in order to find a vertex, we want to use our formula x is equal to negative b over 2a. So we can go from here if you would like, or the original really does not matter at all. Let's go with the original, why not? So we have negative b is 6. So negative 6 over 2 times, and then a is a negative 1. So it gives me negative 6 over negative 2, which is a positive 3. So my line of my axis of symmetry is x equals 3. So I know that for my second parabola, it's going to go through this dotted line, right? Which actually makes sense. I'm 2 away from this dotted line. I'm 2 away from this dotted line. But we still need to find the vertex. So if I know that for my vertex, x is 3, I need to find y. So let's take our equation and plug in 3 everywhere we see an x so that we can solve for y. Doing the math, that gives us negative 9. Then we have plus 18. And we have minus 5. So I find that y is equal to 4 when x is equal to 3. So here's my vertex, 3, 4. Let's go ahead and plot that point here. And now let's connect them. So it's looking like I go through here. That looks good so far. And now I'm going to connect on the other side. And it kind of looks like it goes through that point also. So notice that when we find the points of intersection, we see that it looks like they intersect at the point 1, 0. And it's looking like they cross at the point 4, 3. So my guess is that 4, 3 is actually a solution to both. I know it's a solution to my first parabola. What I'm not certain of is if it's a solution to my second parabola. So when I take x as 4 and I plug it in, I want to check to see that I'm getting 3 as a solution. So we have negative 4 squared plus 6 times 4 minus 5, and it does give me a 3. So, and 4, 3 is my solution. I'll give you a second to digest this information. I know there are a lot of moving parts when you graph parabolas, but it's the same moving parts: x-intercepts, y-intercepts, vertex. And then, of course, because we're looking at 2 of them in this case, we want to figure out where exactly they intersect. And it's nice looking at this graphically, but sometimes it could be challenging because we don't know for certain if they actually cross at that specific point. So we want to make sure that we verify that. Okay. Any comments or concerns right now with relation to this setup? Okay, hearing none, let's turn the page. Essentially what we have on this page, give me 1 second. Guys, relax, it's okay. So essentially what we have on this page is just a review of how to solve quadratic equations. We have our 0 factor property, right? We have our square root property. We have completing the square, Schiltwig, completing the square or quadratic formula. So we have these 4 methods. When we talk about 0 factor property, that's the magic word. We're going to try and factor. Okay. As always, for instance, with this second one, we're going to subtract 2x. So that way we can set it equal to 0, set equal to 0, then factor. We just saw this, and then you would go ahead and you would factor. For chill, for this second set here, we use a square root property. The first thing we're going to do is we want to divide by the coefficient. So we have x squared is equal to 1. That's when we say, let's take the square root of both sides, but we won't forget that that leaves us with a positive or negative solution. So in which case, for our first particular problem, our solutions would be positive and -1. For this second one, we definitely will want to add the 18 first. So we have 5 times x minus 2 squared is equal to 18. We then definitely divide by a 5 because we want to get the squared term completely by itself. Once the squared term is completely by itself, that's when we can take the square root of both sides. That leaves us with x minus 2 is equal to positive or negative square root of 18 over 5, which, by the way, we would rationalize. Okay, we would totally rationalize this. It's not okay to have a square root in the denominator. But to finish this off, we would add 2 to both sides, which means my solution would be x is equal to 2 plus or minus square root of 18 over 5. All right. As a reminder, you don't want to leave a square root in a denominator, except for in Lumen. So when you actually look at these problems in your Lumen assignment for Unit 5, it's going to let you leave a square root in the denominator. So don't worry if it doesn't mark you off, but technically you should rationalize. As a reminder of how to rationalize, if you take that square root of 18 and you write it over the square root of 5, all you have to do is multiply it by the denominator. Remember that? So we multiply by square root of 5 over square root of 5. 18 times 5, that's going to give me 90. So square root of 90 over 5. And then, of course, square root of 90 can be broken down. 9 times 10. So if square root of 90 is the same as square root of 9 times 10, square root of 9 is 3 because 9 is a perfect square. So that gives me 3 square roots of 10 over 5. So my final official answer should be 2 plus or minus 3 square roots of 10 over 5. That's how you would rationalize. And then lastly, we can use either completing the square or using the quadratic formula. We only have 4 minutes left of class, so I want to do a quick recap of completing the square and quadratic formula for you, and then that will end today's session. For the first one, if I want to use completing the square, I must start by dividing every term by my leading coefficient. So that gives me x squared minus 8x plus 7/2 is equal to 0. I'm going to start by bringing 7/2 over, and actually let me write above it, completing the square. Hi, I'm going to start by bringing the 7/2 over. Thank you. So I'll bring the 7/2 over here. So I have x squared minus 8x, leave a little gap, and that's equal to negative 7/2. Recall that we want to write it as the square of a binomial, and we do that by taking half of our b term. So half of negative 8 is negative 4, and then we take that negative 4 and we square it. So negative 4 times negative 4 is a positive 16. What you do to one side, you do to the other side. So we definitely have to add 16 to both sides. So we're going to take a negative 7/2. We're going to add 16. And when we do the math, we get 25 over 2. Okay, notice we have to have the same denominator. If this is over 2, then that becomes a 32. 32 minus 7 is 25. So now that I have x minus 4 quantity squared is equal to 25 over 2, I can now use the square root property. So I'm going to take the square root of both sides, but let me rewrite this so that it's not messy. I'm going to take the square root of both sides. Those cancel, leaves me with x minus 4 is equal to positive or negative square root of 25 over square root of 2. Square root of 25 is 5. So we get 5 over square root of 2. We don't want a square root of 2 in the denominator, so I'm going to rationalize by multiplying by square root of 2 over square root of 2. So that gives me x minus 4 is equal to positive or negative 5 squared to 2 all over 2. And then, of course, we add the 4. So once I add the 4, I found my two solutions. So I've got x is equal to 4 plus or minus 5 squared to 2 over 2. Yes, I squeezed it in there. Whew. That worked. Completing the square definitely has a lot of involvement. There's a lot going on in there. With the quadratic formula, it's a lot quicker. Keep in mind, in order to use it, you have to set your equation equal to 0. So notice that I just brought the terms over. And I'm not going to divide by anything. I'm just going to say that A is 3, B is a negative 2, and C is 4. So now I'm just going to use a quadratic formula. X is equal to negative B plus or minus square root of B squared minus 4 times A times C. I have a feeling that a lot of you prefer this method over completing the square, and you really get to choose your method. This becomes a positive 2. We're definitely going to do the math underneath here. So it's going to be a positive 4 minus 4 times 3 times 4, which is negative 44. And then this is over 6. Clean up what's here. The square root of negative 44, we take out the I first. And then we factor this in 4 times 11, where 4 is the perfect square. So we get 2i squared of 11. So we now have x is equal to 2 over 6 plus or minus. We replace square root of negative 44 with 2i square root 11 over 6. And then, of course, you simplify. Reduce here, that gives us 1 over 3. Reduce here, that also leaves us with 1 over 3, but we can't forget the I squared 11 over 3. And that is how you finish it. So a quick recap of all those techniques. We are going to use them in Thursday's class when we finish our Unit 5 notes. Okay. As a reminder, I will be meeting you tomorrow at 9 a.m. if you would like
Can I
a
see that
review
paper, please?
session. What's that?
Can I see that paper, please?
Yes, yes, of course. So we will be meeting tomorrow for our review session. If you would like to join, come join at 9 a.m. I will stick around until 11 to answer any and all questions. All right, everyone, enjoy the rest of your day. I will see you tomorrow, hopefully, or Thursday. Bye.
Okay, thank you.
All right, thank you.
Welcome. See ya.